Hola clase. Today we are going to see how to work with associated rates of change, or we're simply going to call it rates of change. Now, you may be asking yourself, why so special about rates of change? Because all derivatives are technically rates of change. And what these exercises do is they're going to link how one variable is changing depending on another. And if you think of it, you work with this in the sciences quite a lot, and we're going to basically apply that into our math. So you need to know a couple of things to tackle this. First, you need to know how to form expressions, because these are always going to be word problems. And then you need to know how to derivate, and we're going to use Leibniz notation. So we're going to use it as dy dx because it's much easier to see. All right, how do we tackle these exercises? First, you're going to have to identify what I'm going to call the objective rate of change. So whichever it is that they are asking of you. And they're always going to ask you for it, and you need to know a value. Then you're going to have to link it with a value to find f of x, because you need a function to derivate. Once you've got it, you can derivate. So you can do f prime of x as dy dx. And once you've got that, then you're going to solve by evaluating, because they will have to give you a value. You need to evaluate somewhere. Okay, let's see this in an example so it makes a bit more sense. So they're telling me that I've got a spherical snowball, it's going downhill, and it's getting bigger the more it rolls. They're telling me some relationship, and they want the rate of change of volume with respect of distance. So this is what I want. I want how is the volume changing in terms of, meaning in relation to the distance. That's what I want at a specific point when the distance is 75 meters. So everything that I'm going to do, it's going to be about finding something that I can put in there, meaning finding a volume in terms of distance that then I can derivate. So first I need to begin thinking, what do I know about spheres? And I know the volume of a sphere, that's a formula, and generally if it's a commonly known formula, they will expect me to know it, or if not, they will remind me of it. And this is all very good and well, but this is a function of radius, and I need a function of distance. So this is when this relationship that they gave me comes in handy, because I can substitute and find what I wanted, which was the volume in terms of the distance. So it's simply substitution here. And this is the hardest part, is realizing how to get the expression that you need. Right, now this is going to be a stupidly small number, so I'm just going to simplify it by putting it in the denominator, and it's simply just taking the reciprocal, okay? So it's just a bit tidier. And now I can derivate, which is what I wanted all along. I wanted my rate of change. So I've got my constant here, and then this is a polynomial, and then I'm just going to simplifying here. Let me tidy this up. So this is pi over 16,000 d squared. Now they ask me to evaluate it when that ball has rolled 75 meters. So it's simply going, all right, which is the value when the distance is 75? Well, I'm going to chuck it in here. 75 squared. I evaluate all of that, and it gives me 1.10. And now what about the units? Volume, it's meters cubed. Every distance, which is meters. So this is telling me that for every meter that it advances at that point, the volume increases by 1.110. And that is my related rate of change. So we box it, we're done. Now it's your turn to go and practice. Thanks for watching.